Introduction to exercise 9J, 9K on the product rule and the quotient rule. We're going to do both of them together because they're very similar. But the idea is that we can use the product rule and the quotient rule to make our lives a ton easier. Instead of having to expand or simplify, blah, 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 all those different weird fractions or whatever, we can just differentiate on the spot using the following formulas. Now the product rule, right here, this one right here, says that if we have two functions that are multiplied together and we derive them together, we can say that f dash x times g of x plus f of x times g dash x. So we differentiate one equation, or one part I should say, of the equation, and multiply that by the other part, and then add the original part that we differentiated, but the normal form, times the differentiated part of the other part. Very weird, but that is the formula. In practice, it's super easy. Okay, so let's try to apply our product rule into practice. Can we go to the next page and do question 6a? We're going to go through question 6a together. So, question 6a, of course, you can see that we've got a very complex equation. If we could expand it and then differentiate, but it actually might save us a bit of time to just use the product rule here. So, I'm going to actually first be a little bit pedantic and say, let this equal to f of x, just so I can write f dash x in the future and not have to worry about losing marks. So f dash x equals to, using the formula, now it doesn't matter which order as long as we're consistent, right? Similar to our gradient equation with m equals to blah, blah, blah. I can derive the first part of the equation and multiply it by the second part. So deriving this part here, I'm going to say that's 4x plus, oh sorry, just 4x, my apologies. And I'm going to multiply that by the original part of the second component there. So I've derived the first bit in brackets, multiplied by just the second bit, no deriving. And then I'm going to add the original first part, so 2x squared plus 1, and I'm going to derive the second component, so that's 15x squared. Any questions? And then I can simplify that if I'd like. I can expand that, sorry. I can get 20x to the power 4 plus 64x plus, and then that expands out to 30x to the power 4 plus 15x squared. Any qualms about that? No? I'm just expanding brackets. Great. And then, can I get rid of the brackets? Yeah, I can. Because we're not multiplying anything anymore. Get rid of the brackets. Simplify that. I get 50x to the power 4. Plus, add those together, 79 to x. Oh no, my apologies. That's not an x, so I have to write them separately. So that's 15x squared plus 64x. If you were to fully expand the two brackets there, and then derive it, you end up with the same answer. One more. Let's go through the second part together as well. Again, I'm treating this right here as a component of our equation. So I'm going to say let this equal to f of x, and write f dash x equals to. I'm going to derive the first component, so that's 3x squared, and multiply that by the original 3x minus 5 power of 4. Are we okay with that? Yeah. Just very quick note. Remember, it doesn't matter which order, as long as you derive one, multiply the original, and derive the other, and multiply the other original. Okay, as long as you're consistent. Add. I'm going to keep the original x cubed, and I'm going to multiply by the derivative of 3x minus 5 all to the power 4. Are we okay with that? Now the question is, what is the derivative of that? Now you could write it on the side like I have, or you could just go straight into it, it's up to you. But let's do it on the side here. So the derivative of this is, and hopefully you guys remember this from your chain rule, that's 3x minus 5 to the power of 3, multiplied by the derivative on the inside, so that's 3, so that equals 3x minus 5 to the power of 3. Have I stumped anyone? Okay. I'm going to write that in. 12, 3x minus 5 cubed. I'm going to simplify that. Equals to, you know what, let's not expand. That's a very gross one. It's too powerful. Let's leave it in that form. Let's go 3x squared, 3x minus 5 to the power 4. And then, of course, I'm going to simplify that. I'm going to take the 12 out. Plus 12x cubed, brackets, 3x minus 5 cubed. Any questions? I'm assuming you have your head tilted back because you understand. Thank you. You can see how this is a lot easier than just fully expanding everything out and then differentiating. So that's the product rule. And it makes sense because product means multiply, but quotient rule, of course, means divide. So anytime you're presented with an example that looks like this, you may be better off just to use the quotient rule. So up here is the quotient rule. Just take note of that. Of course, again, if you have a positive in your a plus, in your booklet, just change it to a minus. This one, the rule does matter in terms of the order. This product rule, it doesn't matter because you're going, for example, f dash of x times g of x plus f of x times g dash of x. You could go the other way and say f of x times g dash of x plus f dash of x times g of x, right? It doesn't matter as long as you're consistent. The quotient rule does matter the format, okay? And the reason it does matter is A, because we've got a minus, and B, because the bottom has to be the bottom component of your quotient rule being squared. Bottom component is squared. So, in this example, we're going to follow the same rule. Okay? I'm going to let this equal to f of x. And I'm going to say f dash of x equals to. And I'm going to scroll back and forth so that we're referring to the formula. I'm going to scroll back and say the top equation derived times the bottom equation. So the top equation derived is just 1 times the bottom equation is x squared plus 4x plus 1. Any questions about that so far? No? Okay. Next part of the equation, minus f of x times the derivative of the bottom one. So minus top one times the derivative of the bottom one. So minus the top one, oops, that's a minus 2, times the derivative of the bottom one, which I know is 2x plus 4. Am I going too quickly? Okay. And then referring back to my equation, it's the bottom part that is squared, not the top, the bottom. So then I would write all over x squared plus 4x plus 1 squared. Okay. I'm going to expand and then simplify the top part. So that gives me x squared plus 4x plus 1 minus all of this, which is 2x squared plus 4x minus 4x minus 8. Again, all over, oops, let's do that again. All over x squared plus 4x plus 1 squared. That simplifies to, and of course these two cancel out, and that's x squared minus 2x squared, so that's negative x squared. The 4x is by itself, and then I have positive 1 minus negative 8, so that becomes plus 9, all over x squared plus 4x plus 1 squared. If you're being pedantic, you're more than welcome to take out the negative and write negative x squared minus 4x minus 9 all over x squared plus 4x plus 1, but we are happy to leave it in that form there. Any questions? Okay. Again, you can see how this format is, this rule makes it a lot easier to derive such an equation. Now I know you guys, how much you guys love derivatives of Euler's number, so we'll do an example of that as well, and then let you guys continue on with the work. An example here, I'm not sure if you guys can read that. We've got e to the power of x over e to the power of 2x plus 1. We're going to apply the same rule we did before. So f dash x, I'm going to say let this equal to f of x. Left dash f dash of x, sorry, equals to, again, the derivative, actually I'm going to double check up here, there we go, the derivative of the top part times by the bottom one. So the derivative of e to the power of x we know is just e to the power of x times our original, gives us that, minus the derivative of the bottom one times by the original top one. So I'm going to write original top one times by the derivative of the bottom equation. What's the derivative of e to the power of 2x? Good. Thank you very much. 2e to the power of 2x. And of course I don't bother with the plus 1. And then it's all over e to the power of 2x plus 1 squared. Okay. I'm expanding that out. That becomes e to the power of, what's e to the power of x times e to the power of 2x? Good, thank you very much. E to the power of 3x. We're using our index laws because if we're multiplying and the base is the same, we just add the powers. Plus e to the power of x minus 2e to the power of 3x. All again over, except I'm going to expand it this time. No, you know what? I'm going to keep it in that form. There's not much we can do in expanded form anyway. There we go. Of course, I can collect like terms. And we end up with e to the power of negative, there we go, negative e to the power of 3x plus e to the power of x over e to the power of 2x plus 1 all squared. Again, if you would like to, you're welcome to take out actually, you know what? No, I think that's it. Yeah, we're going to leave it there. If you're being pedantic, you're more than welcome to continue factorizing it, but more cases than not, when it says derive something like this, you're more than likely to use it in application of something else. So in this format, it's fine. Any questions? So quotient rule, product rule. Please note, remember, the product rule does not matter which order you do it in, as long as it's consistent, but the quotient rule definitely matters. A lot of students accidentally do, for example, the derivative of g dash x times f of x, and then minus the other one. Of course, you'll end up with the negative value when you want it to be. Okay.